The problem description and goal for this project is that nowadays the helicopters are a great aid for medical and military use, primordially but not exclusively. Especially in the military, not just the helicopter but any UAV are becoming unmanned. One of the things to take into consideration for that is the stability of the system. Because of that, we want to regulate the speed of the motor of the propeller in order to maintain a stable output from an input even if there is a disturbance. In this case, the disturbance will be an external force that moves the position of the rocker.
This is the block diagram of our model. Our sensor is a potentiometer attached to the rocker that measures its position, and the data is sent to the controller, and it's a reference for the value that we are going to give to the driver. Our driver is an ESC that receives that value and converts it in a PWM for the motor. The motor rotates according to that PWM, and so the propeller. And with the impulse of the propeller, the rocker moves, and so the value of the sensor changes, and it goes on and on. And here is a photo of our model, and you can see here the potentiometer attached to the rocker, and in the serial monitor we send the value for the ESC in form of frequency, and then it sends it to the motor in PWM. So when it goes upwards, moves the rocker, and it moves the potentiometer.
Okay, for this project, we based the characterization of the system. We based on a document that we found on the internet that some student on University of Spain made. So the variables that we need to care about are the mass of the motor and the propeller, the mass of the battery, the mass of the controller or ESC, the mass of the bar or this thing, the angle that we have on rest position, that is that angle, a coefficient of non of roughness, I think. I don't know how to say it. A radius of the axis in here to the motor. Another radius from the axis to the battery. Another radius from the axis to the ESC. Another from the axis to this part of the bar. Another from the axis to the farthest part of the bar, and a radius of the axis to the rock. Then we need to calculate the inertia of all the variables of the bar, the motor, the battery, the ESC, and the rock, and also the torque of all the variables again. For the bar, we need to have some special calculations that we found on internet that have to be with integrals, but it is not too hard. All of the torques are specified with a sen of theta, because we are varying or changing the angle of theta, that in this case, this angle is in rest, and we have a rest angle of 25 degrees. Then again, we can specify the system of the model of the system with this equation: the sum of torques minus the coefficient of rough surface is equal to the total inertia times the angular acceleration. So we can represent this with this notation that is only the derivative of the angular position. So I forgot to say that the coefficient of roughness surface is multiplied by the angular speed. So if we take this to this, we can have all the summation. The thing is that we take care about the most is the force from the propeller to upward. I don't know how to say it, in an upward way, that we will call empuje force. So we have also a torque of empuje, and the function that we will take to the Laplace domain is this one. The radius till the axis, from the axis, this axis to the propeller and the motor, times the force of empuje, the upward force, minus the torque of that force evaluated in some sine of theta. Yes, evaluated in some sine of theta, minus the beta times the speed, minus the inertia times the angular acceleration is equal to 0. Then we will need to linearize this function because it is not linearized. And we obtain that with the Taylor series. And we obtain that with the linearization, the only thing that we get is that the angle sin of theta that we have in here is the rest angle that I mentioned before, that is 25 degrees. So once linearize the function, when we linearize the function, it is like this: the radius from the axis to the motor times the variation of the force of upward force is equal to the total inertia times the angular acceleration plus the coefficient times the variation of the velocity plus the torque of the upward force that I mentioned before, evaluated on the angle of rest times the variation of the angle. And if we take it to the domain of Laplace, we have this same equation, but instead of the derivative things, we have s or s squared. That is the thing that changes when we pass from a function to the Laplace domain. Then we have that the transfer function is the division from the output over the input, and in here the output is the variation of angles that we got in here, and the input is the variation of the force, the upward force. And then we have finally our transfer function, that is the radius from the axis to the last part where the motor and the propeller is, over the total inertia times s squared plus the coefficient of roughness surface plus the torque of the upward force evaluated on the rest angle.
Okay, so now the purpose of this video is to show the real-time graphs or plots of different parameters on this code. First, we have the proportional gain of Kp equals to 0.55, and the proportional and the integral gain equals to 0.2. We have the rest or the initial frequency that we write on the propeller, and a set point just for reference. It's the reference of this potentiometer, and the error is another variable. So in this code, we will show on the serial plot these two parameters. This parameter, sorry, that is the value of the potentiometer. In this case, it's stable, but if I apply a perturbance, it changes, but it stabilizes again without any problem. And I can do this, but it will stabilizes with any problem. Okay, so now I will plot the graph of the error. This is the thing that I am sending to the serial plot, and in this case we can see that is a very low graph, a very with very low parameters. And you can see that again I can modify this, and the error stabilizes again, or I can put it like this and it will go up the reference. Okay, so now we are plotting the value that we write on the frequency with the frequency on the ESC, that is the controller of velocity. We can also do this to modify the writing, but it does not changes very much, and then stabilizes again. So now what we are plotting is oh, I'm sorry, this is printing the past thing that we were seeing on the. Okay, so now what we're doing is plotting the reference. Well, it is not plotting it. We are showing it on the serial monitor, so we are able to change its value if we write something in here like 700, and then we will see this go upward like that, and we can make it a little bit higher, taking care of it, or we can just make it go low like 670, and that's how we control the reference.
This is the part of the code, and here we include the servo library that there's going to use in the ESC as a servo, and it will receive a PWM signal. In the next parameters, we are gonna create a servo object, and we write a proportional gain that is 0.55, integral constant that is 0.2, a variable for the history for the error that is a, y that is for the real value obtained from the potentiometer. The variable pose is to calculate the position of the ESC, and the variable reposo is to reference value in order for the rocker to stay horizontally. The set point is a value that is given by the potentiometer in a certain reference, and this reference we can change it at the end of the code. Next, we write the setup. We attach the servo in the pin 10, and we begin with a serial that is from 9600. Well, in the main program, we are gonna write it in a loop, so this will be constantly decoding, and we are gonna read the sensor that is our potentiometer from the pin A2, and we are gonna write this value in the variable sensor value. And because we are gonna test a real value obtained from the potentiometer, because physically it was placed backwards, so we are gonna take this value minus the sensor value, and we are gonna use this real value, and we are gonna print it in the serial monitor. Next, we are gonna calculate the error that is gonna be the set point minus the value that we already take from the real value, and this error we are gonna use it in the integral part and the compensator part, that is the key P, and we are gonna write it in the pose. And then with this value, the value valor, we are gonna write it in the ESC in these parameters, but we made a security value that if the motor is beyond 87, the ESC we are gonna write it this value, and if it's down this value, we are gonna write the value that we calculate, and in these parameters we are gonna write the error value and a delay of 20 microseconds. And the last two parts of the code is for write a set point that we wanted.